All right, in this problem, I have a particle executing simple harmonic motion with an amplitude of 3 centimeters. So this is a mass on a spring, right? And so the spring is here, and it's bouncing up and down like this, right? So the spring is at a minimum here, and the spring is at a maximum here, right? And it has an amplitude of 3 centimeters, right? So this distance here is 3 centimeters. And I want to know what positive displacement from the midpoint of the motion. So the midpoint of the motion is right there. What displacement from there does its motion, does its speed equal half of the maximum speed? Okay, so this is not as easy as it seems. I mean, it's not terrible, but it's not as easy as it seems. So first, let's think of energy. Let's think of what we know. So remember, I know that elastic potential energy, so this is a spring, elastic potential is 1/2 k delta x squared. And I also know that k equals m omega squared, right? Spring constant for something in simple harmonic motion. The spring constant is equal to the mass times the angular velocity squared, right? So if I take this and I put this into here, right, I can say that the elastic potential energy equals 1/2 m omega squared times delta x squared, right? I just plugged m omega squared in for that k right there, and I have that. So let's look at the energy at the different points, right? So at, let's see, at the maximum displacements, at this point, it's all elastic, and at this point, it's all elastic, and at this point, it's all elastic, right? At those peaks, it's all elastic potential energy. And in the middle, it's all kinetic. Well, it's some combination, right? So this is where it's max kinetic, and this is where it's max kinetic. And so at some point, you're going to have a combination of potential and kinetic, right? So that's going to be somewhere around here. So this is the point we're looking for. Maybe it's like right here, right? And there would be another one up on top, right? Because it's harmonic motion. So we're looking for this distance. I don't know where that's at, but I know at this point right here, it's going to be half kinetic and half, elastic. Okay, so how am I going to figure this out? So I know that if it's half and half, it started with all potential. So I'm going to make an equation that says it goes from all potential to half kinetic, half potential. Okay, so let's make an equation. So it starts right here. It's going to be all elastic potential. And so my elastic potential, it's 1/2 m omega squared delta x squared, right? Like I just said right there. And then over here, it's half and half, right? So that's going to be here. So it's half kinetic. So that's 1/2 mv squared. And it's the other half is elastic, which is just this. So it's 1/2 m omega squared delta x squared. Okay. So now I have this. So let's do some simplification. So all of these have m. M goes away. All of these have a half. A half goes away. So now I have omega squared delta x. Okay, so omega squared delta x squared equals v squared plus omega squared delta x squared, right? And this delta x is going to be the amplitude, right? So I'm going to call this one, my original one, right? That's the amplitude. So I'm going to swap that delta x out for the amplitude, which is, I know that is my amplitude. In mine, it's 3 centimeters, right? So I'm going to say omega squared a squared, so I don't have two delta x's, right? Equals v squared plus omega squared times delta x squared, which is what I actually want. Okay. So now I need to simplify more because I don't know omega. So I do know I do know that v equals negative a omega sine omega t, right? That's our wave equation. It's on the formula sheet. And the biggest sine omega t can be, the biggest this number can be is 1. That's the largest that can be. And so the velocity we're looking at is half the maximum. So basically I'm going to call this, I'm going to call 1. So it just says v equals a omega. And I want the velocity when it's half, right? Half of the maximum speed. So I'm going to take half of this number. So I'm finding v when it's a omega over 2. Right? Okay, so now I'm going to take this, I'm going to plug it in for v. Right? So I'm going to say omega squared a squared equals this a omega over 2 squared plus omega squared delta x squared. Right? Okay. So now, there we go. Look. So if I distribute this square in, omega squared a squared equals a squared omega squared over 4 plus omega squared delta x squared. Omega squared, omega squared, omega squared. It's gone. Got rid of it. Right? So, now it's easy. So now I have a squared equals a squared over 4 plus delta x squared. And that I'm going to leave to you. So if I take this equation and I solve for delta x, right? So this is being added, so I'll give you a hint. You need to subtract this over first, right? You want to get delta x by itself, right? So if you move this over, I already know A is my amplitude that it gave me, right? Just convert centimeters to meters. You can solve this equation for delta x, right? You can do the algebra to do that. At this point, we should be able to do that, right? But we had to do a little bit of algebra to figure this out, and we had to use some wave equations that were kind of new. But now that we're here, you can solve for delta x.